physics students. Today in this video we're going to be talking a little bit about forces and Newton's laws of motion. A lot of this is review from the first physics course you took. But we're going to take an advanced look at some of these things as we move through this unit, which includes Chapter 4 and Chapter 5. The scope of this first couple of videos is going to be just covering Chapter 4 in your textbook. So let's get to it. Let's talk about some of these advanced applications of Newton's laws and forces. Well, the first thing that I really want to do is I want to make sure that we define a force. When we're talking about a force, you may recall that a force is just a push or a pull in any direction. So it is a push or a pull in any direction. The fact that it is a push or a pull tells us that it has a magnitude. And the fact that it'll be in any direction tells us that it has a direction, and therefore a force is a vector. Keep in mind that no matter whether or not you push or whether or not you pull, from the point of view of a physicist, the object, which we're not really going to call them objects, when we start talking about advanced dynamics, and this set of physics as opposed to kinematics is called dynamics. When we talk about advanced dynamics, we tend to treat these as particles on the AP exam. So what you can see is that it doesn't matter if you push or if you pull, the resulting acceleration or velocity of the object is the same, as long as you push or pull in the same direction with the same magnitude of force. The standard unit of force is the Newton. There are actually two types of forces. There are contact forces and field forces. You may recall this from the first time you took physics. Contact requires that the object actually touch another surface or another particle in order for the force to be imparted. Examples of that would be friction or tension, and probably one of the most important ones is the normal force, the force that pushes back whenever you touch anything. So if I touch the table, it touches me back. If I touch it hard, it touches me back equally hard, but in the opposite direction. That's one of Newton's laws, as long as we keep something called an equilibrium, which you may recall is a balance of forces. Weight, on the other hand, is the force of gravity acting on an object, and it's a field force because you don't actually have to touch anything for gravity to affect you. All you got to do is get near another object, and its gravitational field is around it, and you'll be affected by it. The same thing is true for the other three fundamental forces of the universe. The four fundamental forces of the universe are gravity, electromagnetism, and then the strong and weak nuclear force. All of those things, if you think about it, if you get near the Earth, you're going to get into its gravitational field. If you go near a magnet, you're going to be in its magnetic field. If you go near something radioactive, you're going to be affected by its radioactive field. So, all of those things are examples of field forces. Most of the forces we're going to be dealing with are contact forces because electromagnetism gets its own course in AP Physics, so we're not going to talk about that. And radiation, at least nuclear radiation, gets its own AP course as well, called AP Chemistry. So only gravity is largely affecting us as a field force. The rest of them are all going to be contact force. Normal force I already described. Friction just moves in the is always a force that opposes the motion of an object. And finally, tension is a specific contact force where the force is imparted through a cord or a wire or a chain or a rope or some sort of rod, anything where instead of a full surface contact, like your hand touching the board or your hand touching your table, it's only contact at one point instead of multiple points. So tension is something we didn't really talk a lot about the first time we took physics, but we're going to talk a lot about it as an advanced topic in physics. So that's one of the big advanced topics in this particular unit. Okay. So keep in mind that forces are vectors. They can be resolved into their vector components or be the result in a vector addition of multiple forces. There's a special name for this. It's called superposition of forces, and that name is important because it shows up on the AP exam. But if you're doing vector addition, you've got superposition of forces. So superposition of forces is shown here. if somebody were pulling to the right with force 1 and also up and to the right with force 2, the resultant superposition of those forces would be resultant vector R, which is going to be a force that combines both of these. Or if you have just one force, it can be resolved into its components. So you have somebody pulling on a string. In this case, it would be the force of tension. Then there'll be a horizontal component of that force and a vertical component of that force, just like we did with the resolving of vectors when we were talking about things like projectile motion. Whenever you add more than one force together, like we're doing here in B, where you have somebody pulling up with a string and somebody pulling to the right with a string, which what they're trying to say here, by the way, is that pulling up and to the right is the same as if you had two separate hands pulling to the right and up at the same time. But imagine you actually did that. If you actually had a force pulling up and another one pulling to the right, you had more than one force. Well, you can calculate something called the net force, which is the sum of all forces. The notation here is new. This is a notation. It's a summation notation. Right here we can see something that's a little more vector notation. We could even put this in unit vector notation. So the net force is what it always was. It's the sum of more than one force or more than one component of force. And it always gives us some resultant force, and that resultant force is called the net force. So it doesn't matter if you have more than one force, or if you just have one force like you do here, where you know the magnitude of the force which you're pulling with and the angle, you can break it into its resultants. Notice that this could be a pull, or this could be a push, and you're going to get the same resultant net force. So that's reviewed. So there's a pretty good example in your book about superposition of forces. In this case, they're talking about professional wrestlers fighting over the same championship's belt. And in this example in your book, this is example 4.1, the wrestlers are pulling with three different magnitudes, 215 newtons, 50 newtons, and 120 newtons on the same belt. And pretty much what they want to know is, what are going to be the components of the net force acting on the belt. One of the things that's important for you to realize right away for the AP exam is that there are such things as real forces and unreal forces. Each of these wrestlers are applying a real force. That is, each one of them is a real person doing a real push or pull. A net force is never a real force because there's no person, there's no particle imparting the net force. Instead, the net force is an unreal force. It's a force that doesn't have a physical reality, a particle attached to it. It's the sum of the other forces that are physical, that are reality. The reason I mention this is because, from a practical sense, there's a rule that will always get you in trouble on the AP exam. You can only ever put real forces onto free body diagrams. You can never put unreal forces, fake forces, like net force. So basically, don't ever put net force on a free body diagram. It'll always cost you points. Only put real forces. Here we can see that they went ahead and made some free body diagrams of these forces. And when they did, they used some basic trig to figure out what the components of those forces would be. And then they used some of the basic trig we used in the previous unit, Pythagorean theorem, to find the resultants. And they used sine, cosine, and tangent to find the angles or the magnitudes of each of those components. So I like that. If you need a little bit of help remembering how to do that, you certainly can come see me, but it's not that much different than what you were doing before. This is basic FST. Okay, Chapter 4, Section 2. Let's talk a little bit about Newton's laws. The first law I want to talk about, the one that's in Section 2, is Newton's first law of motion. And this introduces the idea of inertia. Inertia, we said, was Galileo's word, and it means to not accelerate. That's what inertia is. So if things have a tendency to not accelerate, they have inertia. So if something's not moving, it doesn't want to move. It has a tendency to not want to speed up, slow down, or change direction, all of which moving would include. So that means that the inertia of a moving object says, I don't want to move. If I'm not moving, I don't want to move. That's what Galileo said, and then later Newton. And then also, if you already have an object that's moving, you don't want it to accelerate. So you don't want it to speed up, slow down, or change direction. You want it to keep moving in a straight line at the same constant velocity. And that's the second part, the kinetic inertia. All right, so one is static for things that aren't moving, kinetic, things that are moving. Kinetic inertia is also called momentum. So when something is moving, it wants to keep moving in a straight line, and it will be very difficult to change it. This is because Newton's first law of motion officially says a body acted on by no net force moves with a constant velocity because it has no acceleration. This goes hand in hand with Newton's second law, which we'll discuss a little bit later. F equals ma. Again, no acceleration means no force. So when we have a body in equilibrium, we know that its net force is going to be zero. That could mean there are no forces acting on it at all, or more likely, there are balanced forces acting on it. And so Newton's first law always applies to things in either static equilibrium or kinetic equilibrium. Static equilibrium means it isn't moving. Kinetic equilibrium means it is moving. And it very likely means it's following Newton's first law. There's a couple conceptual examples I like here a lot. The first one says that zero net force means constant velocity. It's just a logic problem. If this is zero, then one of these two has to be zero. If the object actually is a mass, a particle that has mass, then it can't be the mass that is zero. It must be the acceleration, which means you have constant velocity. In the classic 1950s science fiction film Rocket Ship XM, a spaceship is moving in the vacuum of outer space far from any planet when its engine dies. As a result, the spaceship slows down and stops. Newton's first law says this shouldn't happen. It should keep moving because there are no forces or no significant forces that can stop it. In conceptual example number 4.3, what we see is that constant velocity means zero net force. It's just the opposite. If the acceleration is zero and something has mass, then it must be true that there's no net force. All the forces are balanced. You're driving a Porsche on a straight testing track at a constant speed. You pass a Volkswagen that's much older, that's going much slower, half your speed. Which car has the greater net force? And the key word is net. If you're both moving at a constant speed, you both have no acceleration. If you have no net acceleration, then you have no net force. They have the exact same net force, although they very likely have different amounts of kinetic inertia. They have different momentum. Okay? An important thing to keep in mind here is inertia and its inertial frame of reference. When we talk about something called an inertial frame of reference, what we mean is that something can appear to be accelerating in one frame of reference and not in another. This is an advanced concept. We never talked about this the first time you took physics. So take a look at this example. We have a rider who's in an accelerating vehicle. What we can see is from the point of view of the boxcar, the person is moving. The person is moving from the back of the boxcar here to the front of the boxcar here. But if it was actually not the person that was moving, it was actually the boxcar moving, then what appears to be an acceleration is actually an inertial frame of reference change. So you need to be aware that it was the boxcar that was moving, not the person in it. In the other case, you can see that the boxcar is actually not moving, and we can see that the person is, and so now you're going to get something different. And then finally, in C, the person might appear to be moving left or right with respect to the boxcar, when in fact the boxcar is actually turning. It's actually changing direction. Any of these things could be the effects of an inertial frame of reference, and you need to be aware of that.